Hey guys, in this video I'm going to show you the open and closed sets. So let's first start from the interior points and accumulation points. So what is an interior point? We call a point X an interior point if there exists some epsilon which is larger than 0, such that x minus epsilon plus x minus epsilon comma x plus epsilon is contained in the set A. So let me give you an example. Like this. So A is defined as 2 to 4, and the endpoints are contained in A. So like, if we take X like this, then X is an interior point, because you can check that you can find some epsilon, such that this small set is contained in the set A. So let's say another example. Like if I take y here, y equals to 4, then this point is not an interior point, because you can never find some epsilon such that the small set is contained in A, right? So we can say that X is an interior point, but Y is not. So what is an accumulation point? Accumulation point is defined like this. For any epsilon which is larger than 0, we always have x minus epsilon comma x plus epsilon intersects A minus x is not an empty set. So let me give you some examples. A is still defined like this. So like the previous one, if I take x here, is this x an accumulation point? Well, it is, because you can find some like epsilon, such that there are some points inside the intersection, which is not x. And let's say another example, like if I take A like this. Well, now 2 and 4 is not contained in set A. And still we take x here. Is x an accumulation point? Well, it is still an accumulation point, because you can still find some epsilon. For every epsilon which is larger than 0, you can still find some points here, such that the intersection is not empty. So now let's move on to the concepts of open set and closed sets. So what is an open set? We call a set A an open set. If all its points are interior points. So still, let me give you some examples, like so a set like this. If A is defined as 2 to 4 and the endpoints 2 and 4 are not contained in A, then A is an open set, because if you take any point in it, you can check that this point is definitely an interior point. Say this one, you can find some epsilon, such as this set is contained in the set A, right? So since every point in it is interior point, then A must be an open set. But what about this one? If a set B is defined like this, So the endpoint 2 is contained in B, but 4 is not. Then B is not an open set because you can find some point. You can find a point here. This point is actually not an interior point because, like we did the case before, it's not an. You cannot find some epsilon such that the small set is contained in the set B. So now let's move on to the closed set. We say A is a closed set if it contains all its accumulation points. Let us see some examples, like this one. A is defined as 2 to 4, and 2 and 4 are contained in the set. Then this is a closed set because you can see that actually the set of its accumulation points is just 2 to 4, the set itself. This means the set of all its accumulation points. So you can say A prime is contained in A. So that is to say A contains all its accumulation points. So A is a closed set. Then what about this one? This is a little bit tricky, but you can see here. So now we define B like this. B is an interval 2 to 4, and 2 and 4 are contained in a set, and union single number 1. Is this set a closed set? Well, it is still a closed set because, well, you can compare these two examples, and B is just like have an extra element 1, but you can check 1 is actually not an accumulation point of this set B. So which means the set of the accumulation points of B is actually the same as that in A. So B prime is contained in B. And that is why B is a closed set. Okay, actually, there is another trick to try to figure out whether a set is a closed or open. That is, you can check its complement. If like this, A is open if and only if its complement is closed. So by saying that, I'm not saying that a set being open is the opposite of set being closed. Actually, a set can be both open and closed simultaneously. So there is an example like the real line R. It is actually a set that is both open and closed because you can check that every point of R is interior points. So R is an open set. And also, the set of accumulation points of R is R itself. So R is closed. So we can say that R is both open and closed. So a set can also be not open and not closed at the same time. So just like the example here, B is defined like as 2 to 4, and 2 is contained in a set while 4 is not. So we've already proved that B is not an open set. So is B an accumulation is a closed set? Well, it's not, because actually the set of the accumulation points of B is 2 to 4. And 2 and 4 are both contained in the set of accumulation points of B. So you can see B prime is not contained in B. So B is not closed as well. So we prove that a set can be neither open nor closed. Hey guys, it's me again. Now I'm surrounded by all these sets, A, B, C, D, E, F, G, H, I, J, K. Then now it's your job to find out whether these sets are closed and open.